Like beard.
Did you just compliment someone's beard?
I
So anyways.
complimented your shoes because I actually like them.
Greetings and welcome,
I like
lovers of beards and shoes. You found the right place. That's right. Twin Valley Math Channel, where we talk all things beards, shoes, and today we're gonna dig deep into vectors in three-dimensional space. Of course, still very beard and shoe related. So take a gander at this. Now, you might not be accustomed to 3 dimensions. Maybe you're used to 2 dimensions. I understand that. Don't be afraid. But I've got this little example here to build us up to this concept. And I'm asking us to plot a point in 3 dimensions. So, by the way, this point is an ordered triple, is what you would call this. So it's x, y, z. It seems like ordered pairs or triples are typically represented alphabetically in order, unless sometimes you might see like time and then like dollars. That's an S for snakes per time. And actually I was really worried that S came after T for a second there, but does it? Wait. A-M-N-O-P-Q-R-S-T. Good. All right. Oh, man, that was the best example ever. Well, you know what I'm saying. Sometimes your x-axis might be time, is all I'm saying. So if I wanted to plot this point, the thing I'd want to point out to you first is that x, y, and now our new best friend z have all changed locations. Typically, x used to be our horizontal axis with the positive x to the right, negative x to the left. Now that's the y-axis. All right, we switched it up on you. The y-axis used to be up and down with the positive up and the negative down. Now the y-axis is horizontal, right? And that's all crazy. And the z has replaced the y-axis. It is positive this direction and positive this direction and positive this direction, by the way. But this x-axis, what you're supposed to imagine is that this is like the depth, that it's kind of like coming out at us in some sort of perspective style drawing of like train tracks or something. I don't know. You know what I'm saying. You've taken art class in elementary school. And so the negative x-axis is like going away from us, all right, something like that. So if I want to plot this point, this is what we'll do. I'm going to try to use like 3 different colors here if I can. So x is, I'm going to go negative 4 units. So back away from us 4 units, or back 4 units. So 1, 2, 3, 4. Here's my x so far, right? And then for the y, I've got to go 3 in the positive direction. So that's going to be to the right. So I'm going to go over 1, 2, 3. And now I want to point out that because of this perspective, actually maybe that's a little bit over there. Because of this perspective, if I just drew straight down, I'd be like, that looks like it's like 6.5 on the y-axis. But remember that I'd have to measure it kind of like parallel to this x-axis here, and it would actually land on the 3. Okay, so that's a little unusual perhaps. Right, so there's the y. And then let's say we've got the z, and that's going up 2. So I'm going to go up 2 units from here. And this 2 units is the same height and direction as that over there. All right, so this is where my point would actually be in this kind of 3-dimensional space, so to speak. Now, one of the things you could do to make this a little bit easier is you could kind of draw a box. Let me see, do I have a good color I could use for that? I'm going to use blue. Where I'm going to make a box that goes out this far and then is 3 across, right? And then it's still this far down and like this, and then it's too high, right? And you could kind of draw like a little box if you wanted, right? And it's just going to be in like the corner furthest from the origin of the box, all right? So you can see that it actually would travel the diagonal there, would be the shortest distance to that point rather than following any other direction. So this, by the way, just represents a point in 3-dimensional space, so it's a single point. Now if I was to throw the little angled brackets on it, then I would be referring to the vector whose initial point was at the origin and whose terminal point was at the coordinates there. So that would be referring to the vector, all right? But this one's just referring to the point, so I'll leave it at that. But that's what it would look like kind of graphing in 3 dimensions. I understand that maybe not all of you are masters of perspective, but just do the best you can on that stuff, and you'll do just fine. So let's scroll on down here and talk about vectors in space. So if I want to represent a vector as an ordered triple, that's right, triple, because there's 3 dimensions. It's just suppose point 1, x1, y1, z1, is the initial point of a vector in space, and p2, which is x2, y2, z2, is the terminal point, okay? Similar to what we saw yesterday, except with ordered pairs. It says the ordered triple that represents vector p1, p2 is the following. And notice it's found exactly the same way we did last time, where I just take the second coordinate minus first coordinate, second coordinate minus first coordinate, second coordinate minus first coordinate, and I end up getting my vector represented as an ordered triple, okay? And if I want to find the magnitude of that vector, turns out I can just square root the sums of the squares of all of these expressions, or if like I actually had the numbers that represented these, you could just square those numbers and kind of shortcut that step a little bit. And so magnitude, once again, is still symbolized with the absolute value symbols representing distance, right? And I want to point out that this is literally the 3-dimensional distance formula, and all I had to do was tack on another dimension there, and it's not that bad. And it's also related to the 3-dimensional kind of Pythagorean theorem, so to speak. So let's do an example of this. Why not, shall we, for funsies, right? Because I'm sure you're all very excited about vectors in space. Very excited. So let's see. Write the ordered triple that represents the vector from x to y, and then find its magnitude. So, vector xy with my little harpoon is going to equal the following. And I'm just going to subtract the corresponding coordinates. The terminal vector has its coordinates represented first. All right, so I'm going to do kind of like 4 minus 5, and then -5 minus a -3, and then like a -1 minus 2, right, something like that. There we go. So xy as an ordered triple would be what, -1 comma, that's the same as +3, -5 plus 3 is going to be -2, and then -1 minus 2 becomes more -3. So here's my vector represented as an ordered triple. So if I was to graph that vector, that would be going back 1, all right, away from us 1, left 2, and then down 3. Okay, that's kind of how I could imagine that. So if I wanted to find the magnitude of this vector, all right, that would just be the square root of the sums of the squares of those values. So very similar to yesterday's lesson. So it's not too difficult, I don't think. So let's see, 1 squared is 1, 2 squared is 4, 3 squared is 9. So I believe the square root of 14 is my magnitude. Not that bad. And actually, you know what? I'm gonna draw a picture of this. You guys don't have to, because I know it takes so long just to merely draw this little coordinate plane. Or, coordinate space. That's weird. So the vector is, let's see, like I said, backwards 1, right? And then we'll go left 2, so that's 2 this way. And then we'll go, what, down 3? Let's see, I need something equivalent to this length there. All right, something like that. All right, so the vector itself, kind of hard to imagine here, travels from the origin diagonally to that point. So it's kind of hard to see It's much easier to do this if you have, you know, some sort of computer technology or something that you could. Yeah, CAD would do it well, just fine. All right, but yeah. But yeah, sometimes if you imagine the box that has those dimensions, and the vector is just kind of the diagonal of it, so to speak. So do your best to kind of visualize what's going on there. I don't believe you're going to have to graph a lot of this stuff tonight, but you at least kind of see what it looks like regardless. So let's see. It turns out in 3 dimensions, all of your vector operations are also very similar. So let's do another example here. So let's see. Find the ordered triple that represents 3 times vector s minus 2 times vector t. And then here I gave you the ordered triples for vectors s and t. So 3 times vector s would just be 3 times the vector 1, comma, negative 2, comma, 0. Minus 2 times vector t would be negative 5, comma, 8, comma, 3. Really, nothing too fancy about this stuff. So we are multiplying vectors by scalars, so we distribute. So that would be 3, negative 6, 0. And I actually have the option, I could change this to plus if I distribute the whole negative 2 here. Or I could leave it as minus, which I'll leave it as minus, and just distribute the positive 2. So negative 10, 16, and 6. And then I'll just subtract their corresponding elements. So 3 minus negative 10 is plus 10, which is 13. Negative 6 minus a 16. It's going to become negative 22, I believe. And 0 minus 6 is negative 6. And then if we wanted, we could even find the, magnitude of this resultant vector. So I could actually have viewed this as, right, that I've got like multiple vectors going on here. Technically, you could have done this geometrically with some sort of tip-to-tail, 3-dimensional parallelogram figure, like some sort of polyhedron. But no, thank you. We won't be doing that. We'll stick to the algebra, my friends. And actually, this is almost arithmetic. I don't even know if I'd call this algebra. Please. So this is what we got. We got this like ordered triple going on. So last example. Now, we talked yesterday about unit vectors. And do you guys remember what vector I represented?
1, 0.
The vector 1, 0, it was a one-dimensional vector. Or, well, that's actually true as well. But I guess arguably all vectors are one-dimensional if you think about just in terms of their magnitude. But yeah, it's a vector that has a magnitude of 1 that is in the positive x-axis direction. We had, what was it, the j vector was 0, 1, so to speak, right, which was 1 in the direction of the positive y-axis. And it turns out in 3 dimensions, maybe I should specify that vector I would actually equal this. 1, 0, 0. J would equal, that's a sad harpoon. Come on there. Nope. There we go. Would be 0, 1, 0. And what do you guys, what's this?
0, 0, 1.
What's vector K? And what do you think that represents?
Z.
The unit vector towards the positive z direction, right? Vertical, up and down, or up in this case, right? So if I wanted to represent this vector, AB, first of all, to find vector AB, Man, my harpoons never connect there. I'll subtract their corresponding elements. So I'll do -1 minus 5 is -6. 4 minus 10 is -6. -2 minus a -3 is +3, which I think is 1. Yep. So here's the vector as an ordered triple. If I want to represent the same vector as the sum of unit vectors, all right, that would be -6 vector i's. That would be minus another 6 vector j's. And that would be then plus a vector k, or 1 vector k. And that's represented as the sum of unit vectors. So really, I mean, it's not that hard. It's just a different notation, really, is all it is. Ooh, goodness. Why, thank you. Thank you. And thank you for those of you who wrote bless you in the comments down below. I really appreciate it. So anyways, that'll be all, friends. Thanks for watching. Have a great day. Oh, bless you too, Luke. Wow, man, this is amazing. Just such a generous, kind, courteous. Yeah, everyone's blessed. Bye-bye.